There is something quietly remarkable about the buildings we spend our lives inside. We move through them, through offices and corridors, through kitchens and restrooms, through lobbies and stairwells, and rarely stop to consider what is happening just beneath the surface. Behind every wall, beneath every floor, running upward through every ceiling, there are systems at work. Careful, deliberate, continuous systems that make modern life possible in ways we almost never think about. Tonight, we are going to think about one of them: water. The movement of water through a building is one of the most elegant feats of engineering in the everyday world. It arrives, it travels, it does its work, and then it leaves, carried away just as quietly as it came. Every step of that journey is governed by physics, by careful design, by components chosen and sized and installed with purpose. Pressure keeps it moving. Temperature keeps it safe. Gravity, in many parts of the system, does most of the heavy lifting without any help at all. Commercial buildings, office towers, hospitals, hotels, schools place extraordinary demands on their plumbing systems. Unlike a home, where a handful of people use a few fixtures at predictable times, a large commercial building might serve hundreds or thousands of people across many floors, in many rooms, at many hours of the day. The system has to be ready. It has to be balanced. It has to perform reliably, whether it is the height of a busy afternoon or the stillness of 3 in the morning. And yet, when it is working well, you do not notice it at all. That invisibility is, in a way, the point. A well-designed plumbing system disappears into the background of a building's life. Faucets run when you need them. Toilets flush cleanly and quietly. Hot water arrives in a reasonable amount of time. Drains carry everything away without complaint. The system hums along, pressure held steady, temperature maintained, flow distributed evenly. And the people inside the building go about their days entirely unaware of the careful choreography happening around them. What we will explore over the next few hours is how all of that works. We will start at the very beginning, at the point where water first enters a building from the city supply, and follow it through every stage of its journey. We will learn how pressure is managed, how hot water is generated and kept ready, how fixtures are supplied, and how wastewater is carried away. We will look at drainage and venting, at storm systems and sumps, at monitoring equipment and nighttime operation. We will trace the full arc of water's path through a commercial building, from the underground pipe beneath the street to the moment it disappears into the sewer system below. There is no rush tonight. Each part of this system has its own quiet logic, its own reason for being, and we will take our time with all of it. Let the details settle gently. Let the ideas come at their own pace. The water, after all, is in no hurry. It simply flows where it is needed, steadily and without effort, as it always has. Before any water reaches a faucet, before it fills a pipe or pressurizes a fitting, it begins its journey underground. Beneath the streets of every city and town, there is an extensive network of water mains, large pipes that carry treated, pressurized water throughout the municipal system. These mains are connected to treatment plants and reservoirs, to pumping stations and storage tanks, all working together to keep the supply consistent and safe. And branching off from those mains running beneath sidewalks and lawns and parking lots, are the individual service lines that connect each building to the system. For a commercial building, this service line is the first and most fundamental element of the entire plumbing system. It is typically buried well below the frost line, deep enough that even in winter, the ground temperature around the pipe stays above freezing. The pipe itself may be made of copper, ductile iron, or modern materials like high-density polyethylene, each chosen for its durability and resistance to corrosion underground. The line runs from the municipal main all the way to the building's foundation, where it enters the structure and the building's own plumbing system begins. What makes that water move is pressure. The municipal water system is pressurized continuously, maintained by a combination of elevation, pumping stations, and the sheer volume of water in the distribution network. This pressure is designed not just for one building, but for entire neighborhoods at once. It has to be sufficient to reach upper floors, to serve multiple buildings on the same block, to maintain flow even during periods of high demand across the city. The utility manages this pressure carefully, adjusting it as conditions change throughout the day and night. When the water arrives at a building, it carries that municipal pressure with it. The pressure may vary somewhat depending on the building's location, how far it sits from the nearest pumping station, how high its elevation is relative to the water tower or reservoir serving the area, and how much demand is being placed on the system at any given moment. A building on a busy street near a hospital might experience different pressure characteristics than one on a quiet residential block. But in all cases, the utility is working to keep pressure within a range that serves buildings reliably. That water, as it travels through the service line, arrives continuously. There is no switch being flipped, no valve at the main that opens and closes throughout the day. The supply is simply there, present, pressurized, ready. The building's own systems determine how much of it is used and when. And the moment it crosses beneath the foundation wall and enters the building, it becomes the responsibility of the building's plumbing system to manage it wisely. Just inside the point where the service line enters a building, before the water travels any further into the distribution system, it passes through two of the most important components in the entire setup. They are modest in appearance, a valve and a meter, sitting close together near the foundation. But between them, they provide control and accountability over everything that follows. The first is the main shutoff valve. This valve exists for a simple but essential reason. It gives the building the ability to isolate itself from the municipal supply. In the event of a major leak, a burst pipe, a flood, or any emergency that requires the water to stop flowing. This valve is the mechanism that makes it possible. One action, turning the valve closed, and the entire building's supply is cut off at the source. No water continues to enter. Whatever pressure remains in the pipes bleeds away as fixtures are opened, and the system can be safely worked on. In a commercial building, the main shutoff is typically a large gate valve or butterfly valve, sized to match the service line entering the building. It is located where it can be reached quickly and clearly, often in a mechanical room near the building's entrance or in a dedicated utility space close to where the pipe comes through the foundation. In many jurisdictions, the location of this valve is required to be clearly labeled and kept accessible at all times. It is, in a very real sense, the building's master switch for water. Just beyond the shut-off valve sits the water meter. The meter's job is to measure exactly how much water passes through it, to count every gallon that enters the building and record it accurately so that the water utility can bill accordingly. Meters in commercial settings must handle flows that can vary enormously, from the trickle of a single overnight maintenance faucet to the surge of a busy workday morning when dozens of fixtures are in use at once. To manage this range, commercial meters come in different designs. Mechanical meters use the movement of water to turn an internal mechanism, a series of gears or an impeller that drives a register, much like an odometer in a vehicle. These meters are durable and have been used reliably for generations. Ultrasonic meters take a different approach entirely. Rather than relying on moving parts, they send sound waves through the water and measure how the flow changes the behavior of those waves. From that, they can calculate flow rate and accumulate usage over time. Ultrasonic meters have no mechanical components in contact with the water, which means they tend to experience less wear and can maintain accuracy over longer periods. In either case, the reading that accumulates on that meter represents the total volume of water that has entered the building. Utility workers read it periodically, or in modern installations, data is transmitted remotely, and from those readings, billing is calculated, usage trends are tracked, and unusual spikes in consumption can be flagged for investigation. That meter, in its quiet way, is where accountability begins. Everything the building uses passes through it. Every gallon is counted. Water, by its nature, wants to move toward lower pressure. In most circumstances, that is exactly what we want it to do, flowing from the high-pressure municipal supply into the building, through the pipes, and out through the fixtures. But there are conditions under which that direction can reverse. Pressure in the building system can, under certain circumstances, exceed the pressure in the supply line, and when that happens, water can begin to flow backward, out of the building, and into the municipal system. This is called backflow, and it is a serious concern. The reason it matters so much is contamination. A commercial building's plumbing system comes into contact with all manner of substances in the course of normal operation. Cleaning chemicals, irrigation water, process fluids in industrial or laboratory settings. Even the contents of a toilet system, all of these exist somewhere within a building's plumbing. If any of that water were to travel backward through the service line and into the city's water main, the consequences for public health could be significant. The municipal supply serves not just one building, but many. Contamination introduced at one point can spread widely before it is detected. Backflow preventers exist to make certain that never happens. These devices are installed in the service line close to the point where water enters the building, positioned to act as a one-way gate. Water may pass through in the normal direction, into the building, but it cannot return. The design of the device ensures that if pressure ever reverses, The backflow preventer closes and holds, blocking any backward movement of water before it can reach the municipal main. One of the most common and widely required types in commercial applications is the reduced pressure zone assembly, often referred to simply as an RPZ. The RPZ is a carefully engineered device that uses a combination of check valves and a relief chamber to maintain a zone of lower pressure between the building's supply and the city main. Under normal conditions, water flows through freely in the correct direction. But if conditions change, if building pressure rises above supply pressure, or if either check valve begins to fail, the relief port in the center of the assembly opens and discharges water outward, preventing any backward contamination. It is a system designed with redundancy in mind, because the consequences of failure are too significant to leave to a single point of protection. Because RPZ assemblies and similar backflow prevention devices are so critical to public water safety, they are required by code in virtually every commercial building. And because their function depends on mechanical components remaining in good working order, they must be tested regularly by certified technicians. Testing involves isolating the device and applying controlled pressure changes to verify that each check valve seals properly and that the relief mechanism responds correctly. If a component is found to be worn or malfunctioning, it is repaired or replaced before the device is returned to service. It is quiet work, this maintenance, done periodically, methodically, without drama. But it is the kind of quiet, careful attention that keeps an entire city's water supply safe. Behind a panel in a mechanical room, that assembly sits and does its job, day and night, ensuring that what enters the building stays in the building, and what belongs to the city remains clean and uncontaminated. Municipal water pressure is designed to serve many buildings across a wide area, and that means it is set to levels that can accommodate the most demanding conditions on the network. For some buildings, and particularly for those located close to pumping stations or at lower elevations, the pressure arriving through the service line can be higher than the building's internal systems are designed to handle comfortably. Too much pressure is not simply an inconvenience. It places stress on every component in the system, on pipe joints and fittings, on valve seats and washers, on the internal mechanisms of faucets and flush valves. Over time, excessive pressure accelerates wear, increases the likelihood of leaks, and shortens the lifespan of fixtures and equipment. It can also cause noise. The knocking and hammering that sometimes follows a quickly closed valve becomes much worse when pressure is high. For all of these reasons, bringing incoming pressure down to a controlled, manageable level is one of the first things a building's plumbing system does with the water it receives. Pressure regulators, sometimes called pressure-reducing valves, accomplish this with a straightforward mechanical design. Inside the valve, a spring-loaded diaphragm responds to the pressure of the water passing through it. When pressure rises above the set point, the diaphragm moves to restrict flow, reducing the pressure on the downstream side. When demand increases and pressure drops, the diaphragm relaxes and allows more flow through. The result is a downstream pressure that remains relatively stable regardless of fluctuations in the supply. For most commercial buildings, the target pressure after regulation falls somewhere between 40 and 80 pounds per square inch. At the lower end of that range, there is enough pressure to serve fixtures on higher floors and to maintain good flow throughout the system. At the upper end, fixtures still operate comfortably without being subjected to more force than they need. The specific set point for a given building depends on its size, the height of the structure, and the demands of its particular fixtures and equipment. But regulation alone is not always enough. In tall buildings, those rising many stories above street level, there is another challenge that pressure regulators cannot solve on their own. Water is heavy, and lifting it against gravity requires energy. Every 10 feet of vertical rise reduces pressure by a little over 4 pounds per square inch. In a building of 20 or 30 stories, that loss accumulates quickly. Water that arrives at street level with perfectly adequate pressure may barely trickle from a faucet on the upper floors if nothing is done to compensate. This is where booster pumps come in. Booster pumps are installed to add energy to the system, to take water at the pressure available and increase it to a level sufficient to serve the upper portions of the building. In many commercial installations, these pumps operate automatically, responding to sensors that monitor system pressure. When pressure drops below a set threshold, as it does when fixtures are opened and demand rises, the pump starts and adds energy to the flow. When demand eases and pressure recovers, the pump slows or stops. The smoothness of that response is often managed by a variable frequency drive, or VFD, a device that controls the speed of the pump motor. Rather than switching the pump fully on or fully off, a VFD adjusts the motor's speed continuously, matching its output to exactly what the system needs at any given moment. A pump running at half speed uses significantly less energy than one running at full speed and then stopping. The result is not only more efficient operation, but quieter operation as well. No sudden surges, no sharp pressure spikes, just a steady, gentle adjustment to meet demand as it shifts throughout the day. In very tall buildings, the challenge is addressed in additional ways: intermediate tank floors, separate pressure zones for different levels, but the principle remains the same. Water must arrive at every fixture in the building with enough pressure to be useful, regardless of how far it has had to travel or how high it has had to climb. Once water has entered the building, passed through the meter, been protected by the backflow preventer, and had its pressure adjusted to the appropriate level, it is ready to begin its journey through the building itself. That journey starts with the cold water distribution system, the network of pipes that carries water from the point of entry outward to every corner of the building where it is needed. The main distribution pipe, sometimes called the cold water main, runs from the service entry point through the building's core, typically following the path of the mechanical spaces, the utility corridors, and the vertical shafts that allow pipes to rise through the floors. In a multi-story building, a riser pipe carries water vertically from floor to floor, serving as the backbone of the distribution network. At each level, horizontal branch lines extend outward from the riser, traveling through the ceiling or wall cavities to reach the plumbing fixtures in that zone. This branching structure main to riser to branch to fixture, is the organizing logic of virtually every commercial water distribution system. It allows the system to grow with the building, to serve dozens or hundreds of fixtures from a single point of supply, and to be isolated in sections when maintenance is needed. A valve on a branch line can shut off water to one corridor without affecting the rest of the building. A valve on a riser can isolate an entire floor. The hierarchy of the system creates a hierarchy of control. The pipes themselves may be made from several different materials, each with its own characteristics and appropriate applications. Copper has been used in plumbing systems for generations and remains common in commercial construction. It is durable, resistant to corrosion, and can handle the range of temperatures and pressures found in typical building systems. It is also relatively easy to join reliably, using soldered or pressed fittings that create permanent, watertight connections. Cross-linked polyethylene, known as PEX, has become increasingly common in modern construction. It is flexible, which makes it easier to route through finished spaces without as many fittings, and it is resistant to the kind of scale buildup that can gradually reduce the interior diameter of metal pipes in areas with hard water. PEX can handle both hot and cold applications and is often used in situations where its flexibility offers a practical advantage. In some settings, mechanical rooms, larger commercial applications, steel pipe, either galvanized or black steel, may be used. Steel is strong and handles high pressures well, though it requires more labor to install and is more susceptible to corrosion over time without proper treatment or coatings. Throughout the cold water distribution system, insulation plays a quiet but important role. Cold water pipes passing through warm spaces are subject to condensation, the same process that causes a cold glass to bead with moisture on a humid day. If left uninsulated, that condensation can drip onto building materials, promoting mold growth and gradual water damage. Insulation keeps the pipe surface above the dew point of the surrounding air, preventing condensation from forming. It also helps maintain water temperature in systems where cold water genuinely needs to stay cold, near food preparation areas, for instance, or in buildings where the supply water warms noticeably during summer months. Branch by branch, riser by riser, the cold water system reaches outward through the building. It is a network built for reliability and redundancy, designed so that water is always there when it is needed, always at the right pressure, always ready to serve whatever fixture or equipment calls for it next. Cold water, once distributed through the building, serves many needs on its own. But a great deal of what people require from a plumbing system, hand washing, showering, kitchen work, certain industrial and cleaning processes, depends on water that has been heated. And producing that hot water, storing it, and delivering it reliably across a large building is a system unto itself. It begins with the water heater, or in larger commercial applications, a series of them. In a small commercial building, a single large storage tank water heater may be sufficient. These units work on a straightforward principle. A tank, typically ranging from a few dozen to several hundred gallons in capacity, is filled with water and heated to a set temperature. Gas burners or electric elements apply heat. A thermostat monitors the temperature and the system cycles on and off as needed to keep the stored water at the target level. When hot water is drawn from the top of the tank, cold water enters at the bottom to refill it, and the heating process begins again. Larger buildings often use a different approach. Commercial boilers, high-capacity heating systems that can produce large volumes of hot water efficiently, serve as the heat source, and their output is distributed through a network of piping and heat exchangers that warm the potable water supply. Boiler systems are well suited to buildings with high and variable hot water demand, where a single storage tank would be depleted quickly and insufficient to keep up. Tankless water heaters, also called on-demand heaters, take yet another approach. Rather than maintaining a stored reservoir of hot water, they heat water only as it flows through the unit. A powerful burner or electric element activates when flow is detected, heating the water as it passes through a heat exchanger and shuts off the moment flow stops. This eliminates the energy lost in keeping a large tank of water hot continuously, what is known as standby loss. In the right application, tankless systems are highly efficient. In buildings with simultaneous high demand from many fixtures, they are often used in combination with storage systems to provide both efficiency and capacity. Whatever the heat source, the temperature at which hot water is maintained is a matter of careful consideration. Too cool, and the water may not serve its purpose as well, and more critically, it can create conditions in which harmful bacteria, particularly Legionella, can survive and multiply within the system. Too hot, and there is a risk of scalding at fixtures, particularly in spaces where elderly people or young children may be present. The balance point for most commercial systems is around 120 degrees Fahrenheit at the water heater itself, hot enough to discourage bacterial growth, but not so hot as to be dangerous at the point of use. That last concern, the risk of scalding, is managed at the fixtures themselves through mixing valves. A thermostatic mixing valve blends hot and cold water in precise proportions to deliver a consistent, safe output temperature, regardless of fluctuations in either supply. Even if the hot water in the building's pipes is maintained at a higher temperature for safety reasons, the mixing valve ensures that what emerges from a faucet or shower head is tempered to a comfortable and safe level. These valves are a small but important layer of protection, working quietly at each point of use to keep the system both safe and comfortable for everyone in the building. There is a particular kind of waiting that most people are familiar with: standing at a sink, holding a hand under the faucet, waiting for the water to turn warm. In a home, that wait might last a few seconds. In a large commercial building, without a carefully designed system to address it, it could take minutes. And in a building with dozens or hundreds of fixtures spread across many floors, those minutes of waiting represent both a frustration and a significant waste of water. Recirculation systems exist to solve this problem. The principle is simple. Rather than allowing the hot water in the distribution pipes to cool when it is not being used, sitting static, gradually losing its heat to the surrounding air, a recirculation system keeps that water moving continuously. A dedicated return pipe runs alongside the hot water supply piping, forming a closed loop. A small pump, positioned at the water heater or boiler, draws water through this loop at a slow, steady rate. Warm water that would otherwise cool in the pipes is continuously returned to the heater, where it is kept at temperature, and fresh, hot water is always present at every point along the loop. The effect at the fixture is immediate. Turn on the tap and hot water is there, not after a wait, but right away, because the water in the pipe has never had the chance to cool. This is more convenient for the people using the building, certainly, but it also reduces water waste significantly. Every gallon that would have been run down the drain while waiting for hot water to arrive is saved. In a building with many fixtures operating throughout the day, that adds up. The pump that drives the recirculation loop is typically a small, quiet unit designed to run continuously or on a schedule without drawing much attention or consuming much energy. Its flow rate is low by design. The goal is not to push water through the loop quickly, but simply to keep it moving enough to maintain temperature. Variable speed controls allow the pump to adjust its output based on conditions, and in some buildings, timers or temperature sensors modify when and how hard the pump runs. During overnight hours, when demand is low and less heat is being lost from pipes, the pump may slow or pause entirely. During the busy morning hours, it runs steadily to keep hot water available at every tap. Throughout the recirculation loop, check valves ensure that water moves in the correct direction. These are one-way valves. They open freely to let water flow in the intended direction and close automatically if flow reverses. In a loop system with multiple branches, proper placement of check valves is essential to prevent short-circuiting, where water takes the path of least resistance and bypasses parts of the loop, leaving those areas without adequate circulation. Two other components support the hot water system in ways that are less visible but equally important. The first is the expansion tank. When water is heated, it expands. Its volume increases as temperature rises. In a closed system, that expansion has nowhere to go, and pressure builds accordingly. Without relief, that pressure rise can stress pipes, damage fittings, and eventually trip relief valves. An expansion tank, a small pressure vessel with a flexible bladder inside, absorbs that extra volume as water expands and releases it back into the system as the water cools. It is a small, passive component that works silently, preventing a problem that most people in the building will never know existed. Together, these elements, the recirculation pump, the loop piping, the check valves, the expansion tank, form a system that keeps hot water ready, balanced, and safe throughout the building. The water moves in its quiet loop, hour after hour, maintaining its temperature with gentle persistence. All of the infrastructure we have followed so far, the service line, the meters and valves, the pressure regulation, the distribution piping, the hot water system, and its recirculation loop, all of it exists in service of a single purpose: delivering water to the fixtures where people actually use it. Fixtures are the endpoints of the system. They are where the plumbing becomes visible, tangible, part of daily life. Sinks, toilets, urinals, showers, drinking fountains. These are the moments where the building's plumbing system makes direct contact with the people inside it. The sink is perhaps the most common of all. In a commercial building, Sinks appear in restrooms, in break rooms and kitchens, in laboratories and medical spaces, in janitor closets and service areas. Each one connects to the hot and cold supply lines through a set of shut-off valves. Small, individual valves that allow the sink to be isolated without affecting the rest of the branch. The faucet itself regulates flow through a valve or cartridge mechanism, mixing hot and cold water to the desired temperature and controlling the rate of flow. At the end of the spout, an aerator, a small screen fitting, blends air into the water stream, maintaining the perception of good flow while actually reducing the volume of water delivered. It is a small efficiency that, multiplied across dozens of sinks in a building, adds up to meaningful water savings over time. Toilets in commercial buildings must handle heavy use reliably and consistently. Most operate on a gravity flush principle. A valve opens, water from a tank or pressurized supply rushes into the bowl with enough force to carry waste through the trap and into the drain, and the valve closes again as the system refills. Pressure-assisted toilets use compressed air trapped in a sealed tank to add force to the flush, producing a more powerful evacuation with less water. In high-use commercial settings, pressure assist models are common because they clear the bowl reliably even with reduced water volume. Urinals in commercial buildings have evolved significantly in recent decades. Modern urinals are designed to use very little water per flush, 1 pint, half a gallon, or in some cases, no water at all. Waterless urinals use a special drain cartridge filled with a sealing liquid that allows liquid waste to pass through, while blocking sewer gases from escaping upward. The reduction in water use is substantial, and because there is no flush valve to maintain, mechanical wear is reduced as well. Perhaps the most noticeable change in commercial restroom fixtures over the past few decades has been the widespread adoption of touchless sensors. Faucets that activate when hands are placed beneath them, toilets and urinals that flush automatically when the user steps away, soap dispensers that deliver their product without being touched. These sensor-driven fixtures have become standard in most modern commercial buildings. The reasons are practical. In a high-use public restroom, reducing the number of surfaces that require touching reduces the transmission of pathogens and improves hygiene for everyone. Sensors also prevent the wasteful habits that can develop with manually operated fixtures, faucets left running, toilets not flushed, replacing them with automatic, consistent operation that uses exactly as much water as the moment requires and no more. Each fixture, regardless of its type, connects to two systems simultaneously: the supply system that brings water in, and the drainage system that carries it away. That second system, the drainage side, is where we turn next. Water arrives at a fixture under pressure, does its work, and then must leave. The leaving is a different kind of journey, slower, gentler in some ways, and governed not by pumps or pressure, but by something far simpler and far older: gravity. Drainage systems in commercial buildings rely on the consistent, reliable pull of gravity to move wastewater from the fixtures where it is generated downward through the building and out to the municipal sewer system. There are no pumps in most of a building's drainage network, no pressurized lines, no energy input required. The pipes simply slope, carefully, deliberately, at a grade that keeps wastewater moving steadily without allowing it to stagnate or accumulate. That slope is more precise than it might sound. Too shallow, and the water moves so slowly that solid material settles out and begins to build up in the pipe, eventually blocking flow entirely. Too steep, and the water runs ahead of any solids it is carrying, leaving them behind. The same result. The recommended slope for most horizontal drain pipes is 1/4 of an inch of drop for every foot of horizontal run. It is a gentle but consistent incline, enough to keep everything moving together toward the outlet. As water leaves multiple fixtures in a building, the individual drain lines from each fixture join together into larger collection pipes. Branch drains from a cluster of sinks merge into a larger horizontal drain. That drain joins with drains from other rooms and areas on the same floor. Vertical stack pipes carry flow from upper floors, downward through the building, collecting contributions from each level as they descend. By the time the drainage reaches the lowest level of the building, it has consolidated into the building drain. The main horizontal pipe that carries all of the building's wastewater to the point where it exits beneath the foundation and connects to the municipal sewer. The sewer system beneath the street receives that flow and carries it onward to a treatment facility where it will be processed before being returned to the water cycle. The building's drainage system is, in this sense, the last link in a chain that begins at the water treatment plant and ends there as well. A slow, circular journey of water through the built environment. Throughout the drainage network, cleanouts are positioned at regular intervals and at key locations, at the base of stacks, at changes in direction, at accessible points along horizontal runs. A cleanout is simply a capped fitting that provides access to the inside of the drain pipe. When a blockage develops, as it inevitably does over time in any drainage system, a cleanout gives the maintenance team a point of entry for clearing tools, whether that is a hand snake, a powered auger, or a hydro-jetting system that uses high-pressure water to scour the pipe clean. Without cleanouts, a blocked pipe deep in a building's infrastructure would be extraordinarily difficult to address. Quietly, continuously, the drainage system does its work. Water falls through it, waste is carried away, and the building remains clean and functional, all because of a gentle, patient slope and the tireless pull of gravity. There is a detail in the design of every drain in a commercial building that is easy to overlook because it is hidden beneath fixtures and inside walls, and because it never moves, never makes a sound, and never requires any energy to do its job. It is one of the oldest and most elegant solutions in the history of plumbing, and it works simply by holding a small amount of water in place. It is called a trap. If you were to look at the drain pipe beneath a sink, the curved section that dips downward before rising again toward the wall, you would be looking at a trap. That curved shape, often called a P-trap, for the way it resembles the letter P when viewed from the side, is designed to retain a small, standing pool of water at its lowest point even after everything else has drained away. That pool of water, a few inches deep at most, is doing something remarkably important. It is sealing the drain. Beneath every building's drainage system, and in the municipal sewer network beyond it, there are gases. The biological processes that occur as organic waste decomposes produce methane, hydrogen sulfide, carbon dioxide, and other compounds. These gases exist throughout the drainage network and, given an open path, would travel upward through the pipes and into the occupied spaces of the building. Sewer gas is not merely unpleasant in odor. Some of its components are toxic, and in sufficient concentrations, certain gases are flammable. The water seal in a trap prevents this, because the trap holds water at the point where the fixture's drain connects to the larger drainage system. There is no open air path between the sewer and the room above. Gases cannot pass through water. The seal holds as long as the water remains in the trap, and under normal conditions, that water is replenished every time the fixture is used. Every fixture in a commercial building, every sink, every toilet, every floor drain, every shower has its own trap. Toilets are designed with the trap built directly into the porcelain, part of the fixture itself. Sinks and floor drains have traps installed in the drain line immediately beneath them. But traps depend on something to work properly, and that something is air. When water rushes down a drain pipe, it displaces the air in that pipe ahead of it. In a sealed system, one with no provision for air to enter, that moving water would create a zone of reduced pressure behind it, a partial vacuum. And that suction, if strong enough, can pull the water right out of a trap, breaking the seal and leaving the drain open to the gases below. This is called siphoning, and preventing it is the job of the vent system. Vent pipes are connected to the drainage system at points near each fixture, and they extend upward through the building, through walls and floors, rising above the level of the fixtures, and ultimately passing through the roof to the open air above. These pipes do not carry water. Their purpose is to carry air, to provide a path through which air can enter the drainage system as water flows through it, equalizing pressure and preventing the suction that would otherwise siphon the traps dry. When a toilet flushes or a sink drains, air moves through the vent pipes to fill the space behind the moving water. Pressure in the drain remains stable. The traps throughout the system stay full, and the building remains sealed against the gases that would otherwise find their way upward. Vent pipes emerge from the roof as small, open pipes, unassuming metal or plastic stacks that most people never think about. On a cold night, you might see a faint wisp of vapor rising from them. In a sense, they are the building breathing, exchanging air between the drainage system and the atmosphere in a slow, quiet, continuous process that keeps the interior safe and comfortable. In larger commercial buildings, individual vent pipes from multiple fixtures are often connected together into a common vent system, reducing the number of separate roof penetrations required. Wet venting, circuit venting, and other design strategies allow a single vent pipe to serve multiple fixtures simultaneously, simplifying the network without compromising its function. The goal in every case is the same. Every trap stays full, every seal holds, and the air in every room in the building stays clean. Not all the water that a building must manage arrives through the service line. Some of it falls from the sky. Rain, and the water that comes with it, presents its own set of challenges for a commercial building. A large roof and commercial buildings often have very large roofs indeed, can collect an enormous volume of water during even a moderate rainfall. If that water is not directed away quickly and effectively, it will find its own path. It will pool, it will seep, it will work its way into seams and edges, and eventually into the building itself. Water that seems manageable in small amounts becomes destructive when it accumulates. Storm drainage systems are designed to capture that water and move it away from the building in a controlled manner. It begins at the roof. Roof drains are installed at low points across the roof surface, positioned so that water naturally flows toward them as the roof slopes gently in their direction. These drains connect to vertical pipes, called leaders or downspouts, that carry the collected rainwater down through the interior of the building or along its exterior walls. The drains themselves are fitted with domes or strainers that prevent debris, leaves, gravel, anything that might wash off the roof, from entering the drainage pipes and causing blockages. For a large commercial roof, a single drain is rarely sufficient. Multiple drains are distributed across the surface, each one responsible for a defined catchment area, and together they handle the full volume of water the roof might receive. The sizing of those drains and the pipes below them is based on rainfall data for the building's location, how much rain might fall in a given period of time at peak intensity, and how quickly the system needs to be able to carry it away. Because roof drains can become blocked, and because a blocked roof drain during a heavy rainstorm can result in water backing up and placing dangerous loads on the roof structure, overflow drains are installed as a secondary safeguard. These drains sit slightly higher than the primary drains, so they remain dry under normal conditions. They only come into play when the primary drainage system is overwhelmed or blocked. But in those circumstances, they are essential, providing an emergency outlet that prevents water from accumulating to a depth that the roof was never designed to support. At the base of the building, storm water collected from the roof meets water draining from the surrounding site, from parking lots, walkways, and landscaped areas. This surface runoff is directed towards storm drains that connect to the municipal storm sewer system, a separate network from the sanitary sewer that carries wastewater. In most cities, these two systems are kept strictly separate. Stormwater does not go to the sewage treatment plant. It flows, often with minimal treatment, to local waterways, retention ponds, or groundwater recharge areas. Some buildings go a step further, incorporating systems that capture and store stormwater for reuse. Collected rainwater, held in underground cisterns or surface retention tanks, can be used for irrigation, for toilet flushing, or for other non-potable applications. This reduces both the demand on the municipal water supply and the volume of runoff entering the storm sewer system. Two benefits that become increasingly valuable as cities grow and water resources come under greater pressure. Rain falls, the roof sheds it, the drains collect it, and the pipes carry it away. The building remains dry, its structure protected, its interior undisturbed. It is a system that most people are entirely unaware of until the day it fails, and then its importance becomes immediately and uncomfortably clear. Water, as any building operator will tell you, has a tendency to go where it is not wanted. In buildings with basements, lower levels, or underground parking structures, gravity, so useful in the drainage system above, becomes a liability. Water that drains properly from the floors above can accumulate in spaces below grade, and getting it back out again requires a different kind of system entirely. This is where sump pumps come in. A sump is simply a pit, a recessed area in the lowest point of a below-grade space, designed to collect water that gathers there. That water may come from several sources. Groundwater that seeps through foundation walls and floor slabs, surface water that drains down through stairwells or ramps, condensate from mechanical equipment, or in some cases, the discharge from other building systems. Whatever its source, it finds its way to the lowest point and collects in the sump. The pump installed in that sump is what removes it. Sump pumps are submersible units, designed to sit in the water they are pumping, sealed against the moisture around them. They activate automatically, triggered by a float switch that rises with the water level in the sump. When the water reaches a set depth, the float lifts, the switch closes, and the pump begins to run, discharging water upward and outward through a dedicated pipe to a drain, a storm sewer connection, or a designated discharge point at grade. When the water level drops back down, the float falls, the switch opens, and the pump stops. In critical installations, basement mechanical rooms for example, where flooding could damage expensive equipment, redundant sump pumps are common. A primary pump handles routine conditions, and a secondary pump sits in reserve, ready to activate if the primary pump fails or if inflow exceeds what one pump can handle alone. In some installations, a battery backup system ensures that the sump pump can continue operating even during a power outage, precisely the kind of event that might accompany the heavy rainstorm, causing the flooding in the first place. At the other end of the concern, not water coming in from outside, but water threatening to come in from the sewer, backwater valves provide protection. During very heavy rainfall, municipal sewer systems can become overwhelmed. The volume of water entering the sewer from storm runoff, combined with normal sewage flow, can exceed the system's capacity. When that happens, pressure builds in the sewer main, and sewage can be pushed backward, up through the lowest drain connections in nearby buildings. A basement floor drain, a laundry tub, a lower-level toilet, these can all become entry points for sewer backup if nothing prevents it. A backwater valve, also called a sewer backflow preventer, is installed in the building's drain line as it approaches the connection to the municipal sewer. Under normal conditions, the valve is open and wastewater flows out through it freely. But when flow reverses, when pressure from the sewer system pushes back toward the building, a flap or gate inside the valve closes automatically, sealing the drain against the incoming surge. When conditions in the sewer normalize and pressure drops, the valve reopens and normal drainage resumes. Together, sump pumps and backwater valves address the two directions from which water can threaten a building's lower levels, from below and around through the ground, and from the sewer system beyond. They are systems that wait quietly for conditions that may come rarely or never. But when those conditions do arrive, they are ready, A commercial plumbing system that is functioning well is largely invisible. Water arrives, flows where it is needed, and drains away, and the people inside the building experience none of the complexity behind that simple outcome. But maintaining that seamless operation requires information, a continuous quiet awareness of what the system is doing, how it is performing, and where its conditions might be drifting away from what they should be. Monitoring begins with the most fundamental measurements: pressure and temperature. Pressure gauges are installed at key points throughout a commercial plumbing system: at the service entry, downstream of the pressure regulator, at the discharge of booster pumps, and at various locations in the distribution network. These gauges give building engineers and maintenance staff a continuous picture of conditions throughout the system. A pressure reading that is lower than expected might indicate that a valve has been partially closed somewhere upstream, or that a pressure regulator needs adjustment, or that demand somewhere in the building is unusually high. A reading that is higher than expected could signal that a regulator has drifted or failed. Either way, the gauge provides the first indication that something warrants investigation. Temperature monitoring serves a similar purpose in the hot water system. Sensors at the water heater, along the recirculation loop, and at distant fixture connections give operators confidence that water is being maintained at the correct temperature throughout. Temperatures that fall below the target range can indicate a failing heating element, an imbalance in the recirculation loop, or heat loss from uninsulated piping. In systems where Legionella prevention is a priority, hospitals and healthcare facilities in particular, temperature monitoring is not just good practice, but a regulatory requirement. Flow sensors add another layer of awareness. By measuring how much water is moving through various parts of the system, flow sensors help operators understand usage patterns, detect anomalies, and verify that equipment is operating as designed. A flow sensor on a recirculation pump return line, for example, can confirm that water is circulating properly through the loop. An unexpected flow reading in a section of the building that should be unoccupied overnight might be the first indication of a leak. Water quality is maintained not just through the treatment that happens at the municipal level, but through additional measures that buildings take on their own behalf. In areas where the water supply has high mineral content, high concentrations of calcium and magnesium dissolved in the water, those minerals can gradually deposit inside pipes, on heating elements, and on the interior surfaces of fixtures and equipment. This buildup, called scale, reduces flow, impairs heat transfer in water heaters, and shortens the lifespan of components. Water softeners address this by passing the incoming water through a bed of resin beads that exchange calcium and magnesium ions for sodium ions, reducing hardness and minimizing scale accumulation throughout the system. In some systems, particularly those with older metallic piping or in environments where water chemistry makes corrosion more likely, chemical treatment is used to protect the interior of pipes. Corrosion inhibitors introduced into the water in carefully controlled amounts form a thin protective layer on pipe walls, slowing the gradual deterioration that would otherwise occur over decades of use. These treatments must be managed carefully, the right chemistry, at the right concentration. monitored regularly to ensure effectiveness without introducing their own complications. Through all of these measures, gauges and sensors, softeners and chemical treatments, the system is watched, adjusted, and maintained. Not dramatically, not with urgency, but with the steady, patient attention that keeps a complex system running reliably for decades. There is a particular quality to a large building in the middle of the night. The corridors are quiet. The offices are empty. The lights are dimmed or extinguished. The noise and motion of the working day have faded, and the building settles into a slower rhythm, still alive, still operating, but doing so in a gentler, more measured way. The plumbing system follows that rhythm. As the building empties through the late afternoon and evening hours, water demand falls steadily. Faucets are no longer running. Toilets are flushing far less frequently. The lunchtime surge in the kitchen, the afternoon rush in the restrooms, all of that has quieted. By the small hours of the morning, demand may be a fraction of what it was at peak. The system responds to this shift automatically. Booster pumps, which earlier in the day were cycling regularly or running continuously to meet demand, slow down or stop. Variable frequency drives, which had been running pump motors at substantial speeds to maintain pressure under load, reduce those speeds to match the reduced requirement. The energy the building consumes for water distribution at 3 in the morning is a small fraction of what it consumes at noon, and the system achieves this efficiency without any human instruction. Pressure in the distribution piping, freed from the constant draw of active fixtures, stabilizes. During the day, pressure at any given point in the system fluctuates as fixtures open and close. Each one drawing water creates a momentary dip, and the system works constantly to compensate. At night, with no fixtures in use, that restless variation settles. Pressure holds steady at the regulated set point. The pipes simply full and waiting. The recirculation system continues its quiet work. Hot water still moves through its loop, maintaining temperature in the distribution piping so that the first person to arrive in the morning will not have to wait for warm water. But with less heat being lost to the surrounding air, the building itself is cooler at night and less heat escapes through the pipe insulation. The recirculation pump may run at a slower pace or cycle less frequently. Temperature sensors in the loop detect when the water has cooled to a threshold and prompt the pump and heater to restore it, then quiet again. Storage tanks, if the building uses them, refill during these overnight hours. Any drawdown from the day's use is gradually replenished, and by morning, the tanks sit full and ready again. Somewhere in the background, leak detection systems continue their watch. These systems monitor flow sensors, pressure readings, and in some cases, acoustic sensors that can detect the sound of water moving where it should not be. An unexpected flow, reading in a zone that should be entirely inactive overnight, a branch serving a floor where no one is present, may indicate a leak in a pipe or a fixture that has been left running. The system logs the anomaly, and in buildings with automated controls, an alert is generated for the maintenance team to investigate in the morning. This automated vigilance is one of the quiet achievements of modern building systems. The building watches itself. It does not require a human presence through the night to maintain safety and function. Control systems monitor conditions, make small adjustments, log data, and wait. The plumbing performs its overnight duties, maintaining pressure, keeping hot water ready, monitoring for problems, with the same reliability it brings to the busy hours of the day. The pipes hold their water, the seals hold their gas barriers, the pumps rest and wait. And in the stillness of the building at night, there is a kind of order that is easy to miss, but deeply present. Everything in its place, everything prepared for the day ahead. We have traveled a long way tonight. From the underground service line beneath the street, through the meters and valves and regulators, up through the risers and branch lines, into the water heaters and recirculation loops, out through the fixtures and down through the drains, all the way to the quiet, watchful state of the building in the deep hours of the night. It is a journey that water makes continuously in every commercial building, in every city, every day and every night. And yet it is a journey that almost no one who moves through those buildings ever thinks about. There is something worth sitting within that. The systems we have explored are not simple. They involve hundreds of components, carefully sized and selected and positioned. Valves and pumps and meters, traps and vents and sensors, heaters and softeners and expansion tanks. Each one was chosen by someone, designed by someone, installed by someone, and is maintained by someone. The knowledge embedded in a well-designed commercial plumbing system represents generations of accumulated understanding of fluid dynamics and heat transfer, of microbiology and materials science, of building codes developed in response to things that went wrong and were then made right. And yet the goal of all that complexity is, in the end, simplicity. Water that flows when you want it, drains that carry it away when you are done. A building interior that stays dry, warm, clean, and safe without requiring its occupants to think about any of the mechanisms that make that possible. That invisibility, the way a well-functioning system disappears completely into the background of everyday life, is not an accident. It is the point. Engineers and designers and tradespeople work toward it deliberately. The measure of success is not that you notice how well the plumbing works. It is that you do not notice it at all. Water flows where it is needed. It arrives at the right pressure, at the right temperature, at the right time. It is measured and monitored and kept clean. And when its work is done, it leaves quietly through a system of slopes and seals, carried by nothing more than gravity, toward the treatment facility where its journey will begin again. Each component supports the next. Each decision made in the design of the system ripples through every fixture, every pipe, every drain. The backflow preventer protects the city supply. The pressure regulator protects the pipes. The expansion tank protects the heater. The trap protects the air in the room. The vent protects the trap. Everything connected. Everything dependent. Everything quietly doing its part. There is a kind of comfort in systems like this, in the knowledge that behind the walls of the buildings we occupy, things are working as they should, that water is present, that it is safe, that the infrastructure of modern life, unseen and unheralded, is holding together in the background while we go about our days and eventually our nights. Let that thought settle now. Let the image of it sit gently. Water moving through a building in the dark, slow and steady and unhurried, finding its way through pipes and valves and fittings with the patient certainty of something that has been carefully, thoughtfully designed. The system works. It has always been working. And tonight, as you drift towards sleep, it continues, quietly, reliably, without pause. Water flows where it is needed. The building breathes, and all is well.